Hello everyone, my name is Radostin Stoyanov, and in this video I'm going to talk about our work on multi-tenant programmable switches. In recent years, many applications have been developed for in-network computing based on the much action processing model. Some examples include inbound network telemetry used to collect and report network state, consensus protocols significantly increasing throughput and reducing latency in distributed systems, stateful load balancers capable of replacing hundreds of software instances with a single switch, key value stores providing high throughput and low latency for caching applications, and machine learning applications used for in-network classification or to accelerate training frameworks. In-network computing applications are useful not only because of their increased throughput and lower latency, but also because offloading software functionality to the network allows us to save CPU cycles on the host. However, can we run all these applications on the same switch at the same time? This is not just a matter of switch resources. Data centers are shared by many organizations that have different requirements and that should be transparent to each other while running. So, what does it take to run in-network applications as a service? While Programmable Data Plane Virtualization aims to run multiple in-network applications simultaneously on a single device, the coexistence of multiple tenants on a programmable switch has some requirements. We need mechanisms for security isolation, which we are going to discuss next, performance isolation so that performance of one user application is not affected by other users, and resource isolation so every user has guaranteed an uninterrupted set of resources. In addition, when deploying a new program on the switch using dynamic reconfiguration, the data plane operation should not be interrupted from the perspective of other tenants. As multi-tenancy enables multiple users to share the same physical data plane, there are several aspects we need to consider in terms of security. A malicious user could impact the performance of other users on the switch, for example by continuously cloning and recirculating packets in the pipeline. A malicious user could also impact the functionality of other applications, for example by changing the queue size information before it reaches a congestion control application. Therefore, we need mechanisms to limit the capabilities available to users. Resources such as tables, registers, and counters allocated to one user should not be accessible to other users. We need to ensure that applications are modular and self-contained. When reusing memory, for example in packet queuing, we need to ensure that one user cannot infer data from other users' traffic. We could allocate part of the memory to each user, or make sure that users cannot reference memory that has not been erased. We adopt an operating model of multi-tenant programmable switches that resembles that of host-based virtualization. In particular, we differentiate between network operators and their users. A multi-tenant data plane should allow a network operator to perform a set of actions before and after a user program. This means not only allowing to assign packets to user programs, but also, for example, limiting the amount of outgoing traffic. Protocols such as VXLAN can be used to encapsulate packets, enabling users to modify inner packet headers, while the outer headers are controlled by the operator and used to forward the packet to the correct destination device. This method can be used to abstract the underlying hardware infrastructure and still provide the ability for users to perform arbitrary packet processing. However, to manage a multi-tenant data plane, a network operator might need some additional mechanisms to control what capabilities are made available to users. To support multi-tenancy, we introduce roles and permissions to the data plane. Using roles and permissions allows us to define the level of access available to each program. A role of superuser can be used to define how packets are processed before and after user programs in the pipeline. A user role represents all capabilities available to user programs. A network administrator can define custom roles with specific set of permissions. For example, custom roles can be used by load balancers and multi-level tunneling applications. While the permission to recirculate packets might be necessary for multiple levels of encapsulation, it might not be required for load balancers. To address these requirements, we propose a multi-tenant programmable switch architecture, or MTPSA. MTPSA extends PSA, the portable switch architecture, with the ability to support multiple users and provide security, resource, and performance isolation. This architecture introduces a superuser pipeline, enabling packet processing before and after a user program, that can be used to programmatically associate incoming packets with user programs, to apply packet encapsulation, or any other operations on the incoming and outgoing traffic, such as limiting the input-output ports available to user programs. MTPSA supports multiple user pipelines, each running independently of other users. We implemented a prototype of MTPSA by extending the PSA BMV2 software switch using the P4C compiler. As you can see, a superuser program is used to define ingress and egress pipelines, while user programs are pipelines similar to the simple SUMI switch architecture. They consist of programmable parser, match action control block, and a deparser. A superuser ingress pipeline assigns a user identifier to each incoming packet. It corresponds to a switch context where a user program is installed. By default, the user identifier is set to 0 and the context corresponding to this value is reserved as a control context. A control context is used to process unexpected packets. For example, when no programs have been installed or the received packet cannot be associated with any user. A default action might be, for example, to drop such packets. The ingress pipeline can also be used to programmatically set permissions to each packet using the standard metadata bus. The MTPSA target is using this value to limit the amount of capabilities available to the program processing the packet. The egress parser is applied to packets before the user pipeline and enables packet encapsulation transparent to user programs by extracting the outer headers. The egress match action tables and deparser are applied after the user pipeline. They can be used to process outgoing packets before sending them to the output queues. This method allows us to remove encapsulation headers before sending a packet to a destination server or virtual machine. Alternatively, the egress pipeline can also apply packet encapsulation by adding outer headers to the packet. This approach allows us to provide information such as the user identifier to other devices within the network. To evaluate the hardware feasibility of MTPSA, we further implemented a prototype on the native PGA SUMI platform using the Xilinx 2018 compiler. This prototype allows us to measure multi-tenancy effects such as packet latency, throughput, and resource consumption. Our prototype currently supports up to 8 user programs on the Vertex 7 FPGA, and it could be extended. For simplicity, the user programs are installed between ingress and egress pipelines. We use a single 128-bit metadata bus, from which only 40 bits are made available to user programs. Our evaluation results detailed in the paper show that MTPSA scales with the number of users supporting line rate traffic. MTPSA allows users to define programs with different complexity without affecting the latency experienced by other users. In our evaluation results, each superuser program and user context take approximately 4% logic resources and 6% memory resources. In summary, we propose a methodology for switch multi-tenancy and programmable data plane virtualization. MTPSA offers security, performance, and resource isolation and is capable of processing packets at line rate. Our project is open source and available on GitHub. This includes behavioral model and native PGA implementations, P4C compiler support, and a few example applications. Thank you for watching this video. I'm happy to answer any questions or to engage in a discussion with anyone interested in this topic.